So up until now in the course, we focused predominantly on internal flows. But now in this chapter, we're actually starting to finally look at external flows. And when we're talking about external flows, we're thinking about things like the famous wind tunnels, right? Where you have, say, a car and they have wind going over it at a certain velocity and they're trying to figure out all the aerodynamics and they're looking at the drag forces and the lift forces. And that's where we are in the course right now. And so we're actually going to be looking at a problem where we're calculating this drag force. Now, in our case, we have a silo that's 10 meters tall. The diameter of the silo is 3.5 meters, okay? And we have wind that comes in horizontally at 8.3 kilometers per hour, okay? We're going to assume that the temperature is 30 degrees Celsius, okay? And what we're trying to find is, what is the bending moment? If we have a drag force that's acting on this, what's the moment wanting to turn that silo over? Okay. Now, before I started the problem, I went online, and your table in the back of your book, table 8 and 9, also has this information. Again, I went online, I went to Engineering Toolbox and got this information, but we also can guide this information from your text. And I looked for air. There's a table that will show you different properties of air at different temperatures. So for 30 degrees Celsius, I found that air has a density of 1.16 for kilograms per cubic meter. And I also found what its viscosity, its kinematic viscosity is 1.608 times 10 to the minus fifth. Okay, and I'm going to need that for this example. Now the approach that I'm going to use is I'm going to start by calculating the drag force. And then once I have the drag force, I'm going to go ahead and do basically what we did in statics and take the moments about a point and figure out what the bending moment is. Okay. In this lesson, we learned that the drag force is equal to, let me go ahead and write this down. Okay. So we have the density, we have this coefficient of drag, we have the velocity component, and then we have an area. Okay. So when I look at this problem, first of all, I have to kind of look at what we know. I know the velocity, but right now I have the velocity in kilometers per hour. It's not really convenient because we need to have it in meters per second so that we can work with all the other terms in the consistent units. So the first thing I'm going to do is I'm going to convert that velocity into more commonly used units. Okay, so in an hour, all right, you've got 3,600 seconds. In a kilometer, you have 1,000 meters. Okay, and this gives us a velocity of 2.306 meters per second. Okay, so there's one term here. I've got the density. Again, we looked that up. In your book, it's table A9, but if you didn't have your book handy, you can go online to Engineering Toolbox. There's a lot of different sources. If you just do a search on properties of air, you'll find it. So we know the density. Let's look at this coefficient of drag. Now, in order for us to get this drag coefficient, there's lots of different ways. In your book, they have charts where if you know the Reynolds number, you can get the drag coefficient. There's times where you have to get it from a chart. There's times where it comes from a table. In our case, we have a chart in our book. So I'll just write down the chart. Again, it's in the chapter. We're going to start by calculating the Reynolds number because we're going to need that. We know that the Reynolds number is the velocity times the diameter, in this case, the 3.5 meters divided by the kinematic viscosity. Okay. So our velocity in this case we just figured out was 2.306 meters per second. Okay, the diameter that we're talking about is 3.5 meters. And we're just going to divide that by the viscosity right there. I forgot where I wrote that down. Times 10 to the minus 5. And we have meters squared per second. Okay, so I look at this and making sure my units work out. I've got meters per second times meters is meters squared per second divided by meters squared per second. All the units are just fine. So this gives me a Reynolds number of, 5.02 times 10 to the 5th. Okay. For a Reynolds number of 5 times 10 to the 5th, from our chart, and again, this is in your text, we come up with a coefficient of of drag. CD there's times in our course where it's a discharge coefficient. Later on when we do open channel flow, in this particular case, it's going to be a drag coefficient of 0.35. Okay, so we have pretty much everything. Now the area I'll get to in just a second. So let's go ahead and calculate this drag force. And we'll just plug and chug here. So we know the density is 1.164. Okay, my coefficient of drag is 0.35. I know my velocity term here is the 2.306 meters per second. We'll square that. We'll divide by 2. Multiply it again. We're in SI, so that's 9.81 meters per second squared, right? So we're good with this term. Okay, now for the area term, what we're thinking of when we do the area term is it's kind of like if you're looking at the silo from this perspective, okay? We're really thinking about a projected area. So if you were just looking at the silo, like if you're the wind and you're blowing towards the silo, as weird as that sounds, what you would see is you would see an object that's 10 meters tall and that's 3.5 meters wide. So we're really thinking about the projected area. You don't see that it's a rounded object. All you see is that it's this rectangular obstacle that's 3.5 meters wide by 10 meters tall. Okay. So when I calculate the drag force, I get this to be 37.9 newtons. Okay. So I'll underline that as well. I'm kind of underlining all the important things. Now, the problem required that we calculate the moment that's caused by this drag force. Okay. So if we take a step back and we think about our statics course, we do a little free body diagram. What I've got is I've got, of course, the silo here. Okay. At the base, I'm going to assume this is like a cantilever type of connection, right? It's fixed, where you have a Y, an X, and a bending moment. Okay. We have a force that we just calculated right here. And this was this 37.9 newtons. This is at a distance at a height of 5. Okay, and that's actually 5 meters. I'm kind of tight on space there, but I'll go ahead and work it out. So if I do the sum of the moments about the base equals 0, okay, we see that the moment minus 37.9 newtons at a distance of 5 meters is equal to 0, assuming this is at equilibrium, right? This is basically what's the moment, what would be the required resisting moment so that this silo wouldn't overturn when you have a force of 37.9 newtons. And we get a bending moment of 189.5, and the units on that would be Newton meters. And I'll go ahead and box that in. Okay. So to reiterate, in this problem, what we did is we started with this silo that was 10 meters by 3.5 meter diameter, and we wanted to figure out what the drag force would be from a wind that was coming in at 8.3 kilometers per hour. Okay. We started by looking up the properties of that wind at 30 degrees Celsius, and then we went back to our drag formula. We realized that we needed to get the coefficient of drag, which required us to do the Reynolds number. With that, we pretty much just substituted all the terms in. We figured out that the drag force itself was almost 38 newtons, and then just taking moments about the base, we got a bending moment of about 189.5. And that concludes this example of drag force.